Okay. So we will continue with our class. In the last class, we have learned about the basic concept of boundary layer. Right? We know the boundary layer split the flow over a flat plate between two regions. One is the viscous region, where the Navier-Stokes is applied. The other part is the inviscid region, where the flow will be as it is before it is disturbed, which means the flow is just having a uniform profile, right? Now the problem is the one within the boundary layer, how we analyze it, which equation do we use to analyze it. Okay? Looking back to the boundary layer approximation, it is a very powerful tool, especially on the aerodynamics field. Right? When you design this Audi A8, right, and Airbus, this is where the boundary layer approximation is very important. Okay. Now we need to know the equation that governs the boundary layer, and then implement it to analyze some flow. Okay. Now I give you the bad news. The bad news is, in your introduction to Navier-Stokes, most of the time you are dealing only with one velocity, right? Okay, you are dealing with one velocity, which is u, in the x direction. You never have u and v together. Okay? So this time we will challenge ourselves by having both u and v. Okay? Will it be solvable? Yes, it is. Analytically, it is solvable. The next question is, can you do it? At the moment, I can be 100% sure, no. Right? Now, no. But after this class, some of you, yes. Maybe. Maybe yes, maybe no, maybe do not know, maybe do not care. So, for a very simple cases like this one, you have a layer of fluid, right? And you have flow in that direction and flow in this direction. Okay? So your governing equation become like this. You have u and v. Everything related to the w is gone, right? And the flow is incompressible. That's why you got your rho outside of the equation. And you have steady state. That's why you don't have u over t. So basically we have done all the simplification. Still we end up having this. So to make our life even more simpler, we use the so-called non-dimensional analysis. The one that you use in your fluid mechanics one is the Buckingham Pi theorem, right? That one is one of the many non-dimensional analysis available out there. Okay, the one that we are using now is proposed by Bejan, Adrian Bejan. So if you open a book entitled Convective of Heat and Mass Transfer, you will find this derivation. Okay, other than Bejan, there is one professor in University of Wisconsin, William B. Krantz. He developed his own non-dimensional analysis. Okay, I was in his class when in Singapore last time, so I know this. Okay, so we use that kind of thing. Okay, and from this analysis, actually, if you are smart, you can have your own number, right? Out there, you have your Renault number, right? You have your Nusselt and so on, right? So, if you do that, you non-dimensionalize the component into something that you set it as a basis. In this case, you divide x with L. What is L? L is the length of the domain. We make it curved so that we are not bounded with Cartesian or cylindrical or spherical. But in this case, when you derive it, we are dealing with flat plate. So you have this flat plate, the length is L, right? And the thickness of the boundary layer, you know it is delta. So you define x with L and y with delta. And you do that for all, right? And then you know that boundary layer is very thin. When the boundary layer is very thin, u will be much bigger than the phi. Velocity in the x will be much bigger than the velocity on the phi. Because the other one is very thin, right? U over t, for 1 second, it just go to 1 cm. Because this is the length. You cannot go beyond that. No more water, right? So 1 second, the most you can get is 1 cm. But in this direction, you can have it, u can be 1 meter per second because there is enough length for you to work. Right? So that you can postulate that u is more than phi. Right? U is bigger than phi. And also, because your dy is very small, you divide something with something very small, it will be very big. Okay? When you have that, you will know that whatever divided by dx can be neglected. You end up with having these two. Clear, ladies and gentlemen? This one we haven't done anything. We just take rational. That when you have this thing, u will be much bigger than phi, and d dy will be much bigger than d dx, because x can be very long and y can be very small. So the gradient in the y direction is much bigger, right? Having said that, you can simplify your previous this equation. This one is very small, cancel. This one is big, it's okay. This one is big, this one is small, so you just cancel all those things. You are having this thing. Okay? Now your life is much simpler. Rather than having 3 equations, you have 2 equations. Can you solve it now? Okay, now, luckily, Blasius, one of the Prandtl students, I told you that Prandtl postulated something and his student proved it right. So he is the one who proved it right. So Prandtl postulated that, and then Blasius come up with the so-called similarity variable. So this one is called stream function. You see, for that, you still cannot solve it in terms of u and x. You solve it in terms of pi, psi. Okay, if you plug in here to there, and you know that u is now become this and that, you can solve it using a numerical approach. Okay, now you will not appreciate it, because if you do it now using your phone, you can solve it. But remember, it was solved in 1908 when even your calculator is not there. Right? Even your calculator is not there. So he solved it, right? He solved it and he found out that delta is equal to 5x over Reynolds number x. Okay? Blasius do the calculation. You found that when u is equal to 99% of the u coming, that is where your delta, right? The thickness, the edge of the boundary layer occur when the velocity is equal to 99% of the incoming velocity. That is what you need to do, right? during the technology at that time, which is nothing but his brain, nothing else, he found 5. But then the next researcher found out that the correct answer is 4.91. Of course, that one is not even using calculator also, because when 4.91 was found, it's still there. Okay, so Blasius found it, but the correct answer is 491. So how the hell did Blasius do this?